In the previous video, I looked at one or two proofs by induction concerned with divisibility. Now we're going to look at two more, just slightly more complicated, but not really any more difficult. So here comes the first one. Prove that fn equals 2 to the n plus 2 plus 3 times to the power of 2 to the n plus 1 is divisible by 7. Notice this one says start from n equals 0. We don't always have to start at n equals 1. There is always a choice. So in this case, instead of looking at n equals 1, we should be looking at n equals 0. f0 is 2 to the 0 plus 2 is 2 squared, plus 3 to the 1, that is 7, and that is quite clearly divisible by 7. And so f0 is divisible by 7. Exactly the same as before, we carry on. We assume that the statement of whatever it is that we have that we're trying to prove is true when n equals k. So we're assuming that fk, which is 2 to the k plus 2, plus 3 times 2 to the 2k plus 1 is divisible by 7. In other words, we can write it as 7 times some number. Well, let's have a look here. fk plus 1 minus fk, I've left a space. fk plus 1 is 2 to the k plus 3. 2n plus 1 is 2 times k plus 1, that is 2k plus 2 plus 1 is 2k plus 3. Minus fk, 2 to the k plus 2, plus 3 to the 2k plus 1. Now, in the earlier video, I said that we wanted to choose a number to put there so that we could eliminate the power. Well, here we've got two powers. We can't eliminate both powers at once. It really doesn't matter whether I eliminate the 2's or the 3's. If you're in doubt about that when I've finished, you can try doing it by eliminating the other one. I've got 2 to the k plus 3, 2 to the k plus 2. If I put a 2 there, then the 2's will disappear. So I'm going to eliminate the 2's. We have fk plus 1 minus 2fk, 2 there. So let's work this out. We get 2 to the k plus 3 plus 3. Well, I'm going to write that as 3 squared times 3 to the 2k plus 1. Just check that. 2k plus 1 plus 2 is 2k plus, yes, that works. Minus 2 times 2 to the k is 2 to the k plus 3. Minus 2 times 3 to the 2k plus 1. Now we can see that the 2's are indeed disappearing. I've got 9 of these fellows, minus 2 of them. That leaves me with 7 of them. And once again, my 7 has just appeared by magic. We can now write f of k plus 1 is 7 times 3 to the 2k plus 1 plus 2 times, well, it's 2 times f of k. F of k is 7m. So I can write 7m there. We've got a 7 in both bits. 7 there, 7 there. Quite clearly, therefore, we've proved that it must follow that f of k plus 1 is divisible by 7. And now we just want the last paragraph. We have shown that f0, remember this time, not f1, is divisible by 7, and that if fk is divisible by 7, then f of k plus 1 is also divisible by 7. That means that fn, which is 2 to the n plus 1, plus 3 to the 2n plus 1, is divisible by 7 for all n greater than or equal to 0, where n is an integer, by induction. Our next example looks very similar to the ones we have done, but there is another little complication which occurs with this one. Show that fn, which is 2n plus 1 times 7 to the n, minus 1, is divisible by 4 for all natural numbers. So this time we are starting at 1 again. So we look at n equals 1. If n equals 1, we've got that f of 1, 2 times 1 plus 1 is 3, times 7 to the 1 minus 1 is 21 minus 1, which is 20, which is 4 times 5. And so we do have that f1 is divisible by 4. Carry on. We have to make our induction assumption. We assume that there is some number k, so that fk is divisible by 4 is equal to 4 times m, where m is some integer. Carrying on again, as we've done before, let's look at f of k plus 1. Minus, and we leave a little space, f of k equals, if I put k plus 1 instead of n, I get 2 times k plus 1 is 2k plus 2, plus 1 gives me plus 3. 7, n equals k plus 1, 7 to the k plus 1, minus 1. So there we have f of k plus 1. Subtract, little space again. F of k is 2k plus 1, 7 to the k minus 1. Well, my advice up to now has been to eliminate the power. We can't actually put a number in here which does eliminate the power altogether. But we can simplify things if we take away 7 of these. You'll find that the next line is less complicated because we've lost a fair amount of our powers of 7. Let's have a look at this. This is now 2k plus 3 times 7 to the k plus 1. I'm going to bring in, no, I'll put the minus 1 next, minus 2k plus 1. 7 times 7 to the k is 7 to the k plus 1. Minus 7 times minus 1 is plus 7. Now, if we look at it, we've got 2k plus 3 of these, 2k plus 1 of the same things. Take one from the other, I'm left with 2 times 7 to the k plus 1. And the rest of it is minus 1 plus 7, which is plus 6. We're trying to find a 4. It hasn't actually dropped out yet. But we have got a 2. So let's look at the 2. 2 times 7 to the k plus 1 plus 3. Now, I need another 2. Let's just have a little look at 7 to the k plus 1 plus 3. That is an odd number plus an odd number. Hey ho. Now that is an even number. So that is 2 times something. Let's say 2 times L, where L is a whole number. Now I can write this as 2 times 2L, which is 4L, where L is an integer. Now I've got my 4, so I'm getting happier. So I can now write f of k plus 1 equals 4L plus 7 times fk. Fk with the usual dodge is 4m. So I can write 4m. I've got a 4 in each one, so I can now conclude that f of k plus 1 is divisible by 4. We now write our usual paragraph at the end. We have shown that f1 is divisible by 4, and that if fk is divisible by 4, then fk plus 1 must also be divisible by 4. That means that fn, which is 2 times n plus 1 times 7 to the n minus 1, is divisible by 4 for all natural numbers n by induction. You can find more about this, more examples, in your textbook, FP1, on pages 127 to 130.